In my very first video, I looked at an issue that confused me at university. It was the question of what is the resultant pressure of two streams at different pressures mixing. There were two main takeaways from that video. The first is that each stream needs to lose a different amount of pressure so that by the time the two streams meet, they are both at the same pressure. The way a stream loses more pressure is by increasing its flow. That way, velocity and pressure drop increase. This happens automatically without anyone needing to do anything. Secondly, that mixing pressure, the pressure at which the two streams meet, it cannot be determined by looking at the upstream pressures. Rather, it is determined by the system resistance downstream. If you don't know where the streams go, you can't really say at what pressure they'll mix. If you're designing the system, it means you'll be the one picking the mixing pressure. But there is another scenario we didn't consider, which is the scenario where the higher pressure stream, in this case the 15 bar stream, either blocks off the lower pressure stream at 10 bar or goes even further and reverses flow and starts flowing up to the source of the 10 bar stream. So what are the conditions necessary for this to happen? What we need to consider is how we would make it impossible for the 10 bar stream to flow. The 10 bar stream will not flow if the pressure at the mixing point is higher than 10 bar. How do we get this point up to 10 bar? There are two things that need to happen. First of all, the pressure drop in the system after the mixing point needs to be at least 10 bar. Remember, pressure drop is not constant. Pressure drop through a system increases with increasing flow. We usually call this a system curve. So the flow through the downstream system needs to be high enough such that the pressure drop is at least 10 bar. Secondly, the source of the 15 bar pressure needs to have a high enough capacity to provide the entire flow rate that results in the pressure drop of 10 bar by itself, which means the pump or compressor supplying it needs to be large enough. When we define battery limit pressures in process design like this, we usually assume a constant pressure, and it's easy to forget that the source of this pressure is usually a pump or a compressor with its own characteristic curve. The source pressure usually drops the more flow the device delivers. So our device supplying 15 bar needs to have such a high capacity that it can deliver the flow required to have a pressure drop in the downstream system that is higher than the supply pressure of the other stream. If it is able to deliver even more flow than that, say it can deliver enough flow to create a downstream pressure drop of 12 bar all by itself, then the pressure at the mixing point will be higher than the 10 bar, and the flow would start going from high pressure to low pressure, from the 12 bar to the 10 bar, and then we would have reverse flow. To be able to work out all these details, you really do need to know not only the geometry of all this piping, the pressure drop characteristic of all these lines, but you also need to know the characteristic curves of both devices supplying the 10 bar and the 15 bar. Reverse flow is something we generally want to totally avoid in chemical processes. It can be extremely dangerous. To avoid situations like this, we install non-return valves or check valves onto process lines. These one-way valves mean that no matter how high the downstream pressure becomes, the flow cannot be reversed.